Oliveira. I'm a PhD student at the University of Bozen-Bolzano. So today my talk is flexible aesthetic structures as substrates for resistive pressure sensors. So traditional electronics and sensors have been largely used in the past 50 years. They are very optimized, they're very reliable for a lot of applications. But however, for some applications in which we have very soft materials, they may not be very suitable. That's why in the last 15 years, we have seen a lot of research effort devoted to developing, actually first, why they're not so suitable, because they can be region bulky, they're non-conformable, and they can be non-biocompatible, and also obtrusive. So as I was saying, in the last 15 years, we have some research efforts towards developing flexible and safe electronics and sensors. When compared to the traditional electronics, they can be imperceptible, it can be adaptable, it can be designed to be transparent, and also stretchable. But when we think about stretchability of substrate for soft electronics, there is a problem here, which is related to when we take the substrate and stretch it. And this is, here we have our substrate. I'm representing here in blue our substrate, and the brown structure is the sensor for electronics. So when you take this material and stretch it, this is what we have. We have an elongation in one dimension, but for ordinary materials, we have a reduction in the perpendicular direction. So we call this, as you might know, the Poisson's ratio. So a problem that we have here is that when you stretch your substrate, you're also deforming the sensors and the electronics. And this can be a problem. So you can damage your sensor electronics. You can also influence the performance of your sensors or electronics. And you can also have interconnection problems. So what we have to do here is develop a way to reduce or even eliminate this problem. One approach is to use auxetic materials. Okay, but what is an auxetic material? As you saw previously, if we take ordinary materials, we stretch it, we have this positive Poisson ratio, right? But in auxetic materials, when you stretch the material, instead of reducing in the perpendicular direction, we have an expansion. So the material is designed to behave in this way. It can also be designed to, instead of expanding or reducing the perpendicular dimension, it keeps the dimension. So we call it the zero Poisson's ratio material. And we can see this, some authors in the literature claim that we have this behavior in nature. For example, the cancellous bone, the salamander skin, and some reptiles. We also have the auxetic structures. So among many existing examples, auxetic structures are based on unit cells. So I'm going to present you here two. First is the heat entrance cell. When we apply a force in one direction, in the heat entrance cell, we have the expansion in the perpendicular direction. So we have here two regions with two enlarged regions. But we also have the same heat entrance cell. When we apply a force, we have an enlarged region and a shrinking region. So auxetic structures have also been used in some applications. For example, auxetic outsoles for sporty shoes, inner structures for helmets, and inflexible structures. So our strategy here is to take the same heat entrance cell and use this as a substrate for our electronics, like this. But first, I have to tell you that when we stretch our cell, we have in red our walls, and in this dark color, the hinges. It means that when you're stretching your unit cell or your complete structure, only the hinges are being deformed, but we don't have deformation stretching in the red part, which we call the walls of our structure. So we have here some regions that can be explored to insert, or we can embed sensors here or electronics. And we use this approach, and this is the structure we designed. So we use the same heat entrance cell, and here we see how we are using our structure here. We have our walls, we have our hinges, and we have here an encapsulating structure. If you pay attention to this, you see that our encapsulating structure is positioned in the walls. It means that if we stretch the structure, our encapsulated structure will not be stretched. So this structure can be stretched, can be bent, twisted, and folded. And we took our structure, we stretched it by 76%, we got Poisson ratio of 0.061. It's a zero Poisson ratio structure. And by performing a finite element analysis, we see our encapsulated structure not experiencing any strain. See that the strains are concentrated in the hinges. So we develop also pressure sensor, a pressure sensing material to be embedded inside this encapsulated structure. And our pressure sensing material is a melanoform, which is a very simple material that you can buy on Amazon. We sliced this material, and then we coated this material in a mixture of soap, commercial soap, and carbon black many times, and then we dried this material. So this is before and after the process. And here we have our sensing material inside the encapsulated structure. This gray structure here, this gray color, represents our conductive stretchable ink. So to make the connections of our sensors. And here is a cross-section view of our encapsulating structure. We see here the bands and the lead. So when you apply a force in the lead, you pressure the sensing material, and now you can read the signal coming from the sensor. This is our response time of our sensor for loading and unloading around 50 milliseconds, and the absolute resistance of the material was around 20 megaohms. So this is the final structure here. You see the complete structure with the encapsulated structure having the pressure sensing material inside and the leads. And then we performed some tests. First, we stretch it and shear our material. And while we were doing this, we applied loads. Here we tested 1-to-1 encapsulated structure in steps of 0.02 kilograms from 0 to 0.2 kilograms, and then we unloaded. And also in steps of 0.02 from 0.2 to 0. And here are our results. So we see that for higher loads, we have a divergence in our results. We're still working on that. We're still working on improving our results and also different types of sensors. But we believe that this divergence is related to the assembly of we're still working on that. So in conclusion, we developed this zero Poisson ratio structure that can withstand many types of deformation while keeping the functionality of the sensor. We also developed this low-cost pressure sensing material, which is very easy to fabricate with this response time of 50 milliseconds. And just to give you an idea of what we can do with this material, I give you here two potential applications. For example, we have sportive clothes. So you're wearing your sportive clothes, you're breathing, you're moving. So the fabric is being stretched. And this is what you can do here. You can use auxetic structures to embed the sensors without influencing the results from your sensors when you're using your sportive clothes. And also here, you can use this material for, here's just a basic sample. We have a pack of batteries, and we're using this auxetic material on top of this pack of batteries to get data for the batteries. I mean, if we have a problem in one of the batteries, for example, if one of the batteries starts swelling, it's not going to influence the results of the other sensors because of these auxetic that we have. So thank you very much. Open for questions.